So where we left off is Young had done his one single slit experiment and got that the electrons made a dot back in the back. Exactly expected. If you threw tennis balls through there, it'd be the same thing. But he throws these electrons through two slits, remembering it's a particle. It instead makes a wave-like pattern, as if somehow the electrons forgot that they were a particle and became a wave. This was disturbing. And many people thought it was time to start packing it in because electrons were doing something very bad. Along comes Albert Einstein. Einstein's a clever fellow, and Einstein sits down and says, well, this is explainable. What's happening here is probability. What's happening is the electron might be going through this hole, it might be going through this hole. If you take some math, some fancy math, and you discover interactions between these two spots, you can make the argument that what's happening is the electron is, we don't know exactly where the electron is because of this uncertainty thing that we ran into earlier. So therefore, the electron could be anywhere in this range, anywhere in this range. And so what's happening is if you pretend like the electron is a possibility, mostly here, it could be on this side of the curve, this side of the curve, could even sneak around the edge in some fashion or a tunnel, then you could make the argument that all this is the interaction of the probability of these waves overlapping with each other. Now, it took some hokey math to make that work, but it worked, and Einstein was proud of it. He slapped himself on the back and said, I'd solved the problem. The problem was that there was a set of physicists still scratching their heads saying, it still doesn't seem to make this pattern. It would make kind of like a bright spot, a bright spot, a bright spot, but it wouldn't keep doing this forever. There's something wrong with Einstein's theory. What is the other possibility? Well, the other possibility is a wave, which is interesting because then it might explain this cute little hokiness here. And by the way, some people still believe that. They say it's string theory, and that is a discussion. We'll get to it in a little bit, but not right now because that's not what happened next. What happened next is a group of physicists got together in Copenhagen, and they wrote down all the possibilities following the mandates of Sherlock Holmes. Sherlock Holmes says you write down everything that's possible, you eliminate everything that's possible, and whatever's left over is the truth. And so what they were struggling with was this idea. So they said, okay, we'll accept Einstein's one possibility. We'll accept that the electrons could actually be waves. Seemed unlikely, had no media. Also, by the way, it has mass that moves, really hard to strike. And by the way, when it strikes the tube in the back, it strikes it in one place. Waves don't do that, right? Waves would spread out. And so it kind of didn't work. That didn't mean that it was perfect. It just meant that was another probability. Then a group of physicists at the Copenhagen Convention said, there's one other possibility. And it's hard to imagine, but what if it's not just us that doesn't know where the electron is? What if the universe doesn't know? What? What if the universe doesn't know where the electron is? Well, that's just dumb, right? Well, if the universe doesn't know where the electron is, what happened is it goes through the two slots, is the electron would possibly be anywhere in this range as it comes through this one, right? Or possibly this range, right? Now, this part of the electron, this high probability, would repel this one, so it would drift this way. But this probability would repel this one, which would cause it to drift this way. And it would act just like these probability waves interacting with each other would act just like waves. Because their maximum minimums would appear very much like this. Over here, this idea over here. Now, to presume that, you'd have to say that the electron itself doesn't know which hole it went through. That it actually repels itself. That makes no sense at all. The electron's either here or here. It can't repel itself because it can't be both places at once. Even doesn't know where it is, it can't do that. But just bear with me a little bit longer. Now, Einstein noted that the math for this was beautiful. It worked. It worked better than his model. So he said, look, you know what's interesting? Apparently we, that's us, we don't know where the electron is. So our pattern we get from our experiments ends up looking just like the universe doesn't know where the electron is. The Copenhagen people were like, is it possible, though, that it's not just we that have the problem? How would you test such a thing? So there's much discussion on test the thing. And during the next year, Young comes up with the answer. Young does his experiment again with the two slits. He gets the same picture he had before. It's a beautiful thing. He's got electrons striking the back. Here, 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 here. Looks just like the double slit pattern. Everything's great. And then he does something truly awful. Around one of these slots, he wraps a coil of wire. Now, why wrap a coil of wire? Well, because when you wrap a coil of wire, when an electron goes through here, it creates a magnetic pulse. That magnetic pulse would not change that electron at all, but it would tell you where the electron is, right? It would light up some bulb here, and you go, aha, the electron went through that hole there. The moment you set this up, you get two dots on the back wall. You get two bright spots. The moment you tell where the electron is, moment the experimenter knows where the electron is, this pattern goes away and it becomes two dots on the wall. Two dots on this glowing bulb. Or if you fire one electron at a time, this one glows, then that one glows, and this one glows, and that one glows. Instead of when you fire one at a time through a double slit, they end up making dot here, then dot here, then dot here, then dot here, more dots in the middle, less dots out here, but dot making the same pattern if you wait long enough for it to happen. The moment you know where the electron is, it changes the answer. Why? The only explanation that anybody's come with so far is when the electron goes through here and it lights up the little bulb, you also tell the universe where the electron is. The electron has to decide where it is. It's either going through here or going through here. Once it knows which one it went through, once it lights your little bulb over here, then you know where the electron is. If you know where the electron is, it can't interact with each other because it knows it's not over here anymore. So the universe truly doesn't keep track of all these little things like electrons. In fact, it doesn't keep track of anything. The only thing it keeps track of is when light or something strikes something, it says, oh, it's there. In between these times when these events where it discovers something happens, in between those times, it's not keeping track. The universe doesn't care where things are. To put on a grand scale, and again, this is silly talk, but let's talk about silly talk. Let's say you parked your car up in the upper parking lot. You went to Mr. Rezzi's classroom, you're hanging around there, and for some reason, nothing, no bit of light, no person looking at it, nothing strikes your car. Your car, the universe would lose track of your car, and your car would move. The probability of your car would grow. Your car is sitting right here, the probability would grow. If it kept track of the car next to it, well, it can't run into the same car next to it, so therefore the cars would drift apart from each other. Why? Because, well, they can't run into each other. As it probably gets more and more in the middle, they'd want to get away from each other. And so you'd have to go out there, you look at your car, oh, there it is. Oh, it moved over half a spot, I'm okay. Go back into your car room, sit around. And if you send a little radio message, beep, beep, to your car, lock the doors. Oh, the universe has to know where the car is to make that happen. Oh, your car is going to be locked in place for the moment. But the longer you wait without an observation, the more that electron or your car is likely to drift and disappear and go somewhere else. So the crazy talk. The crazy talk is this. It appears that the universe is not keeping track of electrons. Now, I will say this in its own defense. Einstein said, that's nonsense, can't be happening. It's not going to happen. That's ridiculous. Einstein results to the following. For those of you who believe that pseudoscientists are religious, Einstein's final argument is God wouldn't make the universe that way. He used that twice, by the way. And both times scientists seem to think he's wrong. But the bottom line is, he's convinced this is just a measurement error, that we will get over this someday. But every time we do experiments, we discover something weirder. Let me go a little farther. We sent out a satellite a long time ago, attached to the International Space Station. What it did is it did the following. It created a little zone with magnetic coils around the outside of it to do what? What it was trying to do is try to figure out this area of space to see if there's electrons in it. And it tried to measure where the electrons are. And like, no big deal. Who cares about that? This is a really fun experiment. But here's what they were looking for, and this is the strange part. The universe isn't keeping track of electrons, and electrons could randomly appear if you're looking in a place. Right? They could just appear. And so this nice little satellite went out there, measured this zone of space, waited a long time, and yet, sure enough, electrons appear and then disappear, appear, disappear. Well, no big deal. If you keep staring at a place, something's likely to appear. If you don't stare at it, it's likely to disappear. So another experiments have been done. You've probably heard Schrodinger's cat. Put an electron inside of a box, and you shrink the box down by cutting it in half. Here's the problem. If the box is too small, the electron can't be in one side or the other side because of the uncertainty principle. So what happens? Well, if you put a coil around here and a coil around here, guess what you'll discover? The electron spends half its time on this side, half time on this. The box is separated. You can even move these two boxes apart, and still the electron spends half its time in here, half time in here. Get frustrated? Smash a box. To smash a box, the electron will either appear, now that it's free, or will appear in this box, angry, and tunnel out. Those are your two choices. It'll be in one of those two boxes when you're done smashing it. But until you know which side it's in, it'll act like it's in both, even if you move them apart from each other. And then finally, why does an atom act the way it does? The reason why an atom acts the way it does is because these electrons are really close to each other. They don't know where each other are. So you're asking them to get close to each other. They're not sure where each other are. So how do they deal with that? Well, one way to deal with it is have one spin one way, one spin the other way. That way I know that's the other electron. This is me. Okay, fine. You be on that half. I'll be on this half. We're fine. But these electrons spread out, and when they spread out, they fill up the whole entire shell. The electrons essentially create a field all around outside until something happens. These electrons are actually everywhere inside that shell. And the reason why they can live with each other is because one's upside down. You flip one over, this one either has a flip back or has to leave. They either have to, one or the other, right? Because otherwise it doesn't know whether it's this part, this is me, or is this part of my electron. I don't know which one's part of my electron. So one has to be flipped so we know. So I know you can stay on that side, I can stay on this side, and we don't run into each other. And that's why electrons come in pairs, and that's why electrons come in pairs close together, and that's why you can't get them any closer than that. And that's why shells have to be separated, because you can't have an electron in the middle, because who knows where that thing would be. They want to get to the nucleus. The closest they can get is where these two are. The next shell is the next closest place you can get. That's it. So the bottom line is, a lot of the craziness of the universe, a lot of quantum mechanics boils down to something very, very strange. The universe is not keeping track of your electrons, and until a random bit of light hits them or a human being experiments on them, we're not keeping track. The universe doesn't know where they are. And so there's probability going on all the time. As Einstein put it in his frightening thing, he said, God's not standing around with dice waiting for you to perform your experiment to tell you where your electron is. The answer to the question is God might not be, but the universe is not deciding where electrons are. It's not rolling the dice of probability until something forces it to keep track of that electron. And that is the answer to the question of what the basis of quantum mechanics is. I will continue this lecture on the next one, but this is enough for today.